It's really my honor to make an oral presentation. My topic is Influence of rapamycin on cellulose production and cell growth in Tracy IUT-3 My contents mainly include three parts: background, results, and summary. Firstly, background. Cellulitic fungi have evolved an excellent capability to secrete cellulose to convert insoluble polysaccharides into fermentable sugars for surviving and poor conditions. They have developed a complex regulatory machinery to coordinate nutrients for growth and hydrolytic enzyme production. For instance, the cellulose production of traces is regulated in response to various environmental stresses, such as light, organic solvents, and metal ions. Several signal pathways like MAPK pathways, calcium responsive signaling pathway, and light regulation pathway have been reported to be involved in the regulation of cellulose production. So a better understanding of regulatory systems for cellulose production is a prerequisite for exploitation of such regulatory networks to increase enzyme secretion, improve fermentation efficiency, and reduce the enzyme production costs. The Tau signaling pathway is regarded as a central signaling hub integrating cell growth and metabolism with environmental inputs, including nutrients and growth factors. In response to nutrients, it activates anabolic processes like protein, lipid, and nucleotide synthesis and suppresses catabolic processes such as autophagy, thus promoting cell growth. Several studies have reported that the Tau signaling pathway plays a part in regulating cellulose production. However, the relevant study of the Tau signaling pathway in filamentous fungi is lack. The Tau is first identified as targets of rapamycin. Rapamycin is a lipophilic macrocyclic lactone. It displays antifungal, anti-cancer, and immune suppressive activities. When diffusing into the cell, rapamycin forms a complex with FKBP12, which subsequently binds to the Tau and inhibits their functions. Both FKBP12 and Tau are conserved from fungi to human. Rapamycin is an indispensable tool for studying the role of the Tau signaling pathway in organisms. However, the impact of rapamycin on traces and the cellulose production in filamentous fungi has not been reported as far as we know. So as a first step towards understanding the role of the Tau signaling pathway in cellulose production, the impact of rapamycin on traces grown on different carbon sources was investigated in terms of cellulose production, morphology, cell growth, sporulation, and lipid contents. Traces was insensitive to rapamycin, and only a temporary effect was observed with a high concentration of rapamycin at the early cultivation stage, including decreased cellulose production, cell growth, and sporulation, and altered cell morphology. The molecular mechanism behind this phenomenon was explored by comparative transcriptional profiling and gene knockout of FKBP12. So the next part is results. First one, rapamycin at high concentration temporarily inhibits cellulose production. We first investigate the effect of rapamycin on cellulose production of Tracy IUT-3. In the presence of 0.01 micromole rapamycin, all the tested cellulose production was not was not changed at 24 hours, but was increased at 7 hours and the later hours. Nevertheless, when the concentration of rapamycin was increased to 1 micromole, a serious reduction on cellulose production was found at the early fermentation process. But tracer has the ability to recover and produce the same or even a larger amount of cellulose at 1.68 hours, regardless of the concentration of rapamycin. Obviously, rapamycin improved the cellulose production at low concentrations, but at high concentration inhibit severely the cellulose production at the early stage, which was recovered at the late stage. A similar effect of 100 micromole rapamycin on the cellulose production was found in traces growing on glucose or lactose. Obviously, the effect of rapamycin on the cellulose production in traces was not dependent on the carbon sources, though some subtle differences were observed among different carbon sources. Next, we evaluate the effect of rapamycin on the morphology of trace IUT-gum-cysteine cultured in different carbon sources by confocal laser scanning microscopy. The morphology of trace IUT-gum-cysteine was not affected at low concentration of rapamycin. But when the concentration of rapamycin was increased to 1 micromole, the abnormal hyphae morphology was observed at the early stage. You can see the filamentation of trace IUT-gum-cysteine was strongly inhibited by rapamycin, showing swollen hyphae. However, the morphological defects was not found when at 72 hours. When at 100 micromole rapamycin, only a few hyphae exhibit abnormal morphology at 72 hours and then disappeared after then. All these findings implicated that rapamycin suppresses the hyphae formation in the early stage, growing on cellulose temporarily. Even at high concentration, it can be stored at late stage. When growing on lactose or glucose, there was no notable effect of rapamycin on the morphology of trace IUT-gum-30. Next, we found rapamycin hinders cell growth and sporulation, tentatively, but not the lipid content. We can say the cell growth of traces on cellulose lactose or glucose at 24 hours was retarded notably with the treatment rapamycin at the concentration no less than 1 micromole. But the cell growth impairment was rescued completely at a later stage and cellulose or glucose condition, but not under lactose condition. Meanwhile, the small amount of traces growing on cellulose, lactose, or glucose was also reduced at 24 hours, which was recovered at 180 hours with no significant change, even at high concentration. There was no significant difference in the fluorescence intensity and the lipid form between rapamycin-treated traces and the untreated one, which was independent of the carbon source, implying that lipid synthesis in tracer was not affected by rapamycin. Next, we performed an RNA-seq analysis to gain insights into how rapamycin influences tracer at the transcriptional level. We can say the enriched molecular function was mainly related to catalytic activity, cellulose binding, cellulase activity, and beta-glucosidase activity. The enriched cellular component was mainly extracellular region, and the most enriched biological process was carbonyl catabolic process and cellulose catabolic process. And the most enriched KEGG pathway was biosynthesis of secondary metabolites, biosynthesis of antibiotics, starch and sucrose metabolism, and the next two. We also see that the DJs involved in cellulose production were downregulated by rapamycin. Among the 39 DJs involved in the cellulose production, only AJL1 was downregulated. This is in agreement with the decreased cellulose production and the protein secretion. And as tau is the target of rapamycin, we also analyzed the expression level of the tau complex. We can say that the tau only was slightly downregulated, and the other parts of tau complex was not changed at mRNA level. Also, we found a series of genes involved in tau signaling pathway, but all of them were not significantly changed. As FKBP12 is the cellular receptor of rapamycin, we also confirmed if it is the cellular receptor of tracer. So we knock out FKBP12 and investigate the cellulose production and the cellulose condition. We can say that knockout of FKBP12 didn't impact the cellulose production. So it demonstrates that FKBP12 was indispensable for the temporary inhibition effect of rapamycin on cellulose production in tracer at the early cultivation stage. It is worth noting that knockout FKBP12 alone led to a delay in cellulose production, similar to that caused by high-dose rapamycin. Thank you.